Welcome, Trinity, to NTI Day. Today is February the 11th. First thing that you need to know is the day that you return, we are going to have the test. We will also have a vocabulary quiz that we missed today. So it's very important that you take the steps to make sure you watch this full video and that you do the practice problems. All right, so we're going to start with a review. You're going to need to stop your video for just a second and write these notes down and then come back to the video when you're done. So as a review, there is a difference between this lithium and this lithium. We call this the lithium element. We call this a lithium ion. Okay. More specifically, this is called a cation because it has a positive charge. It lost one electron. Over here, the difference between these two is this chlorine element and this is our chlorine ion. More specifically, an anion because it's negatively charged and has gained one electron. The ions will be attracted to one another. Remember that this is unstable as it is. This one's unstable as it is, so they lose or gain electrons to become more stable. They'll be attracted to one another and they will form this compound in this particular instance. This is lithium chloride. It is an example of an ionic compound. Note that the compound itself is neutral. There are no charges in the compound. And the reason why is because of the electron transfer. So remember that this symbol, this oxidation number here, tells you that lithium is going to lose one electron and chlorine is going to take that electron. So the formula itself will be neutral. One thing that we haven't talked about that is really important and you need to know before you take the test is that all ionic compounds are called salts. So when you hear the word salt, you're thinking table salt. And it is a salt, but there's a gazillion salts. So like this is also a salt. And every single formula that you've written for this chapter is called a salt. Every single name that you've written for this chapter, they're all salts. So salt is just like a name for a large family of compounds. All ionic compounds are called salts. Okay, now what we're going to do is we're going to go back and we're going to look at the properties of ionic compounds one more time. Today, what we're going to do is we're going to remind ourselves what the properties are, but then we're going to go into an explanation of why do they have those properties. So your title here is just going to be properties of ionic compounds. Try to stop and think about what those properties are. You need to know them. One of the properties that we talked about is high melting point. Now, the last time that we really talked about this and took notes on it was our last NTI day. So, high melting point. Now, we did demonstrate this in the lab. So the day that we went into the lab and we did the strength of ionic bonding lab, where we had the two strings, one a normal string, which was our control, and then we had our string that we had soaked in sodium chloride or a salt or an ionic compound. It could have been any ionic compound, but I chose table salt. And then we dried it and you burned the two, okay? If you think back to that and try to picture what that looked like, the string that had the sodium chloride on it, the sodium chloride never melted. So you could see that the sodium chloride turned dark, but it stayed a solid because they do have high melting points. So we did demonstrate that in that lab. You have to know why they have a high melting point, and it's going to come down to the structure. So when we're talking about an ionic compound, they have a structure that's called a crystal lattice. And here's what a crystal lattice structure looks like. Okay, I'm looking at this one right here. Okay, so when you think of like any kind of ionic compound, and we'll go back to sodium chloride again since we're familiar with that, you think like sodium and chlorine, and you probably only think of one sodium and one chlorine. But the fact of the matter is there's a lot of sodium and chlorines that are bonded together in salt. So this would represent sodium, chlorine, sodium, chlorine, sodium, chlorine. And if it is an ionic compound, it's going to form this structure right here, okay? And that's called a crystal lattice structure. That structure itself gives reference to that high melting point. So the reason why they have a high melting point is because of this crystal lattice structure, okay? So the crystal lattice structure is equivalent to or equal to strong bonds. If it has strong bonds, it will resist melting. So we'll say that the strong bonds result is an increase or high melting point. So if we're talking about the crystal lattice structure and strong bonds, we have to talk about energy as well. So the next thing that we're going to talk about is lattice energy. How much energy does it take to break a bond? Okay, when you think of lattice energy, that's what you need to think. So these go together. We have strong bonds. How much energy does it take to break the bond? Okay, now keep in mind that these atoms on the periodic table are not all the same size. So some are larger than others. Okay, so if you have large atoms versus smaller ones, and you don't have to draw this, you just have to be paying attention here, okay? If you have large versus small, the bonds that are holding those together are going to be different as well, okay? So if you have large atoms, you're going to have, like, if we picture this pencil as a bond, or the amount of strength pulling that together from the electrons, okay? Think of it as a larger bond because we have larger atoms. If you have smaller atoms, you'll have a smaller bond. Okay, so again, we're picturing these as the length of a bond that's holding the sodium and the chlorine together, or two other metals and nonmetals. Okay, now think about if it's a strong bond, it's difficult to break. Okay, so it takes a lot of energy to break it if it's a small bond. I want you to think about the difference of being able to break this pencil. So if I hold this pencil, it's going to take some energy. Remember, we're thinking of this as a bond, but I can break the bond. I can break the pencil. Versus, what if I had a smaller bond, a shorter bond? Would it take more energy or less energy to break this bond? And the answer is, it would take more energy to break this bond than it would to break this bond. Okay, so we can reference that back into these thoughts here. The larger the atoms are, the easier or the less energy it takes. The smaller the atoms, the smaller the bond, and the more energy it takes. You got to have a picture in your head or you won't remember this. Okay, so lattice energy. It's defined as the amount of energy needed to break a bond. And I'm going to shorten this amount to AMT. If you're not going to remember that, write the whole word, please. Amount of energy needed to break a bond Okay, now this is going to be to break a bond in this crystal lattice structure, okay? So just kind of keep that in mind. It's the lattice energy. How much energy does it take to break a bond in this crystal lattice structure? Okay, and here's what we said. So this goes with the energy. As size decreases, so let's say as size of atom decreases, the lattice energy increases. In other words, it takes more energy to break this bond than it does this bond. As size of the atom decreases, lattice energy increases. because bonds are stronger and shorter. Okay, we're going to look at one more property today. Another property that you wrote down that day that we had NTI and we haven't talked about yet is that ionic compounds will conduct electricity when they're dissolved in water. So we're going to say conducts electricity when dissolved in water. And only when dissolved in water. They will not do this when they're solids. Okay, so the best way to explain this is to draw a picture. So we're going to start with a salt or an ionic compound, and we'll do the one that we're most familiar with, which is sodium chloride. So that is the way that you would write the formula for sodium chloride. So picture having a bunch of table salt in your hand. Okay, now a little bit underneath that, I want you to draw a beaker full of water. I'm going to go ahead and label that so it's clear what this is. This is a beaker of water. Okay, just stop the video whenever you need to and then restart it. So what we're going to do is we're going to take this sodium chloride and picture yourself dropping all the salt in that beaker of water. So we're going to draw an arrow to show that. We're going to take our salt and we drop it in the beaker of water. Now, something unique happens. I don't know how unique it is, but something unique to ionic compounds happens when you put an ionic compound in water. Okay, so here's what happens. It does something that's called dissociation. It dissociates, or the other word for that is it turns back into ions. So instead of staying like this in this neutral compound, instead it's going to turn back into the individual ions that made up that compound. Now that's called dissociation. So let's say it dissociates, and that would be a better term here. Okay, and that means it forms ions again. We'll just say it forms ions. Okay. Now, you'll have to think back to previous discussions about electricity that we had and what electricity really is. So before, like back in semester 1, we defined electricity as, and the answer was moving electrons. Electricity is just electrons that are moving in a certain direction, okay? So when we have ions, and remember that process of ions, one's giving up an electron and the other one's accepting the electron. We have electrons in the solution, okay? So the reason why this conducts electricity, but this doesn't, is because we have ions here. So we're going to say electricity equals moving electrons, which equals ions. Okay, now for the test, you are going to have to be able to explain some things. So when you're studying, make sure that you are not only practicing your skills, so you've got out pencil and paper and you are practicing writing formulas and you're practicing naming formulas, but you also go back and make sure that you know the mechanics of how and why we have ionic compounds, what their properties are, and you can explain why their properties are that way. I'll put more information in Rockspace for you. Have a great day.